Before the break, I just stopped talking about features and descriptors. And we saw that the Harris descriptor, a corner detector, is good at following these corners, but we don't have a good way to describe them yet. Something like looking at the shape of it or something like that. So this is what is addressed by a lot of key descriptors, key point descriptors. An algorithm that is commonly used is called ORB, which is a combination of two other descriptors. And we're going to look in specifically on the brief descriptor, how that is producing uniquely identifiable corners in the image. And and here you can see an example of the descriptors. Actually, I put the equation how it's done on the next slide. But we have a certain number of descriptors uniquely identified. They got different colors, and what it looks like is something like this. It's actually a bitmap, bit pattern, and it describes the neighborhood of each of these key points. And well, that one I didn't want to show so much actually, but it's some graphics way to display and make a nice graphic. So we just skip that one. The important thing here is we have our modification of the bone image, which is slightly displaced. It's plus 15 and minus 15. And we also apply the median filter because, as you know from the filtering lecture, high-pass filters, they are pretty sensitive to noise. And that can produce a lot of unwanted corners in the data. So it's mostly relevant to apply some kind of low-pass filter before you do this corner detector. So Harris is a high-pass filter as such. And from this data, this one. So what the brief descriptor is doing is looking at the neighborhood of every pixel that we had identified as a peak. So that is the pixel X is the peak position of a Harris corner point. And then we look in the neighborhood, the size of the neighborhood we have to decide. But anyway, if the pixel of X is less than, the center pixel is less than the pixel in the neighborhood, then we put a 1 in this descriptor. If it's greater than the neighborhood pixel, then we set a 0. And that gives us this bit pattern that we use. And here is a small code to actually identify these corners. And what we're doing in this function is first we create a brief instance that is the unit that will compute the brief corner descriptors afterwards. Then we go into the images. We have 2 images, one original and one displaced. And we compute the corner image for each using the corner Harris function, which is a part of scikit image feature. And from that, we identify the coordinates of each of these corner peaks. And then we extract them, extract the descriptors using this brief extractor using image and the coordinates, and that produces key points and descriptors. And after that, we use this long function, show matches, and it shows that it's actually found 2 points here. This one, which matches on that one, and this one, which matches on that one. So at least we found 2 points which match relatively well. And here, as you can see, there are a lot of key points, but there are only few that really match well. And that's something we want to improve in the next step. And the reason for this may be noise. It can also be that image is rotated, and that is something that the brief descriptor cannot handle, rotations. And now it doesn't want to move. So now it moves. So instead, we can also try using the Orb Descriptor, which is an extension of the brief. And the R in the orb is actually rotation. So it's more rotation insensitive and therefore also more robust. And here you can see, first of all, there are a lot of matches. Maybe in the beginning, it doesn't look so much making sense, but you can see that the main matches, they're actually pretty horizontal, which is to be expected because we only had a small displacement. But there are some that actually found the wrong places, so they're going a bit more across. But now you can see also we have many, many more good hits, matches with the same description pattern in the descriptor. And all those where we have matches, they are reliable enough to be used in displacement field characterization. Another topic we can work with is average flow. So there is some kind of movement within the image when we have displaced it. And we can do it in different ways, computing some kind of spatially, so averaging over regions. We can also do averaging over time and a combination of them. And here is a piece of code that in the end, what it does, it's taking these cell items and produce a data frame that describes the displacements. And the average displacement we have in the simple cell image was -1, -1, as you may remember. And for spatially averaging, then you look what's happening in space mainly. And you have several images and you look more or less to average about what's happening on each frame. And an example of that is we can compute the average. This is not so nice code to read. I got it from my colleague and it takes some time to understand, I must admit. But what we get out is that we have an average field of -1, -1. And by plotting it, we can create, we have an X position field, we have a Y position field, and here we have the displacement field that is produced from this. And you can see that the whole average field of the image is pointing -1, -1. And if we draw that as a vector field, you can see all the arrows, they're pointing slightly -1, -1 downwards to the lower left corner. Another way to average is doing it in time. Here we actually compute the average displacement at each time point, and that produces us a little list. And we can see that first of all, we have for frame index 1, we have -1, -1. Then we have for frame index 1, so everybody actually -1, -1. Because that was the motion we had. And we can see here that the average is plotted like this. And if we plot them as a vector field, you can see that every time step has a diagonal -1 displacement. The most complicated is, of course, combining the two. And here we extract a time frame, and then we compute the spatial distribution around that. And with it, we can now actually see how the the field is moving across the different different time frames. And that corresponds then to the stepwise movement across the image. If we do a longer series on this, we can look at a little bit more complicated thing. I have created here something that is moving not only diagonally, but stepwise up. And actually it moves down to the lowermost position. So it's kind of rolling over the edge. And analyzing this, you can see that we track nicely these points. And that can also, of course, be analyzed using the spatial averaging. And that displacement field is more complicated, as you can see. It's not so obvious, really, how things are moving around. And in particular, confusing is that we did this roll over the edge effect. And that gives us also these long, a little bit more hard to interpret edges in this plot. We can also look at the temporal averaging, and we can see that x is going to -1 every second time. So it's doing -1 and then no displacement, -1, no displacement, etc. The y is going from -2, no displacement, -2, and then it does a +1, 2. And looking at the vector plot here, you can nicely see how the field is moving around. And combining the two things, you can see also that it's flip-flopping between the two directions in the frames. And so it's moving a little bit away and it's flip-flopping. And the problems we have when we're doing this kind of tracking is, of course, the noise, but it can also be limited field of view or depth of field. Depth of field is particularly for microscopy. But limited field of view is when items are going out of the screen and coming back again. So it's ideally you should keep your moving items within the same frame. Otherwise you can have problems, but there are also other problems that due to the noise, you may not do the same segmentation of the objects every time. Can also be that now we have only looked at kind of well-behaving objects. It could also be that the objects are splitting or merging. And then is the question how you should track those objects. That's not obvious always. So there you have to find strategies how to handle that. So that is, and also objects can just die or reappear. That's also what can happen. So tracking is not an easy task. That's requires some planning, both already on the experiment side, but also in the analysis. You have to really make sure you have an algorithm that can handle all specific cases that you are working with. Here is a simulation example to look at what happens when things are moving a little bit. So here we are talking about jitter or motion noise. It can be that due to the high resolution, things are not stable. They can vibrate a little bit. I yesterday talked to a colleague who had problems that when he was working with high resolution, they could see the air condition going on and off in the experiment. And yeah, that's a problems that you also have to consider in the experiment planning. And in principle, what we have is we have the sample moving around, but there is an additional random magnitude and angle of the object that you have to consider in this tracking. And there are some limitations. We can also look at so flow rates, how far away can the object move and still be detectable. Also, what kind of flow, how much how do it behave? Density of objects. Again, in this case, we have only been looking at single objects well distanced, but it could also be that things are moving crossing path. So which one is going in the right way? That needs to also be included in the tracking model. It's not, okay, say, all of a sudden degrees to what it was moving before. That means we had a crossing and you did a crossover between two items. So that's also something to take into account that I forgot to mention before. And another problem is how unique each object is. It's in particular, if you have crossing objects and you have very similar objects, it's harder to detect than if you have one that is more oblatoid and the one is more spherical, then it's easier to identify which one is going the right way. How we can improve it? Well, we can, of course, increase the acquisition rate. With that, we are less sensitive, but also the jitter may be averaged out if you do longer exposure times. So then the object will be a little bit more blurred, but you don't have much zigzag motion of the object. The resolution, well, of course, depends on how much you have in the image, how small the objects are, and what rate you want to they appear. And from the experiment point of view, you can play with different setup parameters like the pressure, flow rate, and type. You can also play with the particle uniqueness, and of course, check that you don't have too much vibration and temperature changes. And of course, the mixture of the objects can also have an effect on how well you can track the objects. So a lot goes back to the experimental part, how you can optimize your experiment still to keep it making sense for your investigation, because otherwise you make something that is more hypothetical because it's not looking like what you really want to know. So you have to vary things within the boundary of what your investigation actually asks for, and find a sweet spot which is good for your detection and for your analysis. That actually goes back to the experiment planning, to put the right questions and plan the experiments and include the analysis into the planning. Here is a simulation example where we have some particles moving, looks like bombs in rainbow colors, but it's particles that are moving around. And in this case, we have a motion vector going in of some jitter on the motion, and that you can see as this is a little bit. And still, it was pretty good in this case to track these, identify and track these objects. Here again, we are lucky that they are not overlapping, except for this one is critical, this in the corner. But otherwise, there is no problem with overlapping tracks. Yeah, so how can this simulation help us to improve the experiment? For one thing, it can actually help us decide what concentration of items we want to use and still be able to detect things. And also match the frame rate versus the flow rate. And also have an idea how robust you are for this jitter. And with that, we hopefully can design a better experiment. And at the experiment time, again, as I said in the beginning, you have 2 or 3 days of experiment time, and then it really has to work. And not that you will sit another 2 years on just finding a solution to help out what you didn't plan for at the experiment time. So it's better to have a well-planned experiment, in particular when you do dynamic experiments, to plan it well and make sure that you have the right parameters for working with it. And of course, we have the statistical questions. What information do you want to measure? The error in the bubble position, depending on different things, like in terms of 5%, less than 5% of the flow field, or 20% in topology. We can also look at 5% error in shape or volume, looking at distribution changes and individual bubble changes, or even looking at strain tensor calculations. There are many parameters that you have to decide what are my criteria to accept this as a good experiment and also as a good analysis. So all these numbers you have to define as someone is coming in or out. Yeah, I don't know. I think someone didn't mute the microphone. So what we can do, we can add a lot of parameters in the tracking. We can have the nearest neighbor tracking, looking at just, oops, this one is not on anymore. Ah, there it is, yeah. So nearest neighbor tracking, just looking at find the nearest. We can also looking at that's the same thing. PI. Okay, so we have PF following and PI following. Now what's now PF and PI? Sorry, I have lost something here. You can You can also look at the maximum displacement between different objects. So there are different neighborhood extensions to combine if it's just a neighbor in the current case or if it's following the first image or the last image. No, so we have I1 here and I2. So one is outgoing from the initial, and the other one is going back and checking back to the previous. And with that, you can improve your neighbor information. Then we can even include more predictions in it with some offsets. We know that it has a motion field of some speed. And then we can say that, okay, if I have point here and the previous motion was in that direction, then it's likely that we have next point here, and that can improve also the tracking. And this is actually very helpful. And not only that it can say that we have a constant distance, but it can also be predicted by the trajectory of the course. And then, of course, we can add on physical models, and we can even use Kalman filters for the particle tracking. So these are statistical models to optimize the a posteriori probability of the positions. And then we can also, of course, work with other principles. with nearest neighbor, we have a good starting point, but we can also work with different hypothesis testing methods. And as I said before, we have some shortcomings with merging and splitting particles and appearing and disappearing objects. And here, to solve it, one way is to look at the shapes, and the other way is also looking at what are the physical requirements for the objects to be identified. A different way of identifying the flow and the displacement is to use correlation, cross-correlation, where we compute the cross-correlation between image at time 0 and image at time 1. And that can also be done with some displacement to check around in the neighborhood. And this correlation is usually some multiplication approach, but more efficiently, you can also use the Fourier transform. And the way to compute the correlation, cross-correlation, is to compute the Fourier transform of the first image and of the second image. And the second image is actually complex conjugate. And when we do that, we can, as in the one-dimensional case, I just produced 2 peaks here with some displacement. I think the displacement is 6. And then I cross-correlate these two. And the output of the cross-correlation is a very strong peak 6 positions away. So the green one here is just a 0 position, the starting point, and this is the displacement. So that's actually a pretty good tool to identify where you have displacements. And of course, it also works in 2D. Just have to use the 2-dimensional Fourier transform. And here we use the a 5 out of the MNIST written number database. And we can see that if we are moving around, this is the, say, domain, then we move around the 5 and see where we have a hit in the object. This is mostly more time consuming to do, so that's why it's easier to work with the Fourier transform. And what we also can work with is not only just doing the correlation, we can also look at the mean squared error when we do this kind of scan, or root mean squared error, and looking for the minimas in this scan. And that would be something like this. Let's see, this is not a movie, but the problem is we may land in cases where we have there is a local minimum, but I don't think it's a good one, actually. It's a strange place. And we can also work with structural similarity indexing. There are many metrics that to compare images and local positions. And here is the case using the Fourier transform. And as you can see, it's a bit confusing because we have one position here and we have another one here. And the case is actually, this is a quite symmetric shape. So if we are at the corner, it can be that it actually grabs the top and lower part and correlates with that. And that is what you can see in this plot here, but it actually grabs the right position. We can try it with this piece of bone slice. This is not an easy task to register because it's almost a random pattern. But we have taken a region out of about this area here, and that is what is extracted. And now we want to find where it is located. And even looking at it in more detail, you can see we can move around with it and see if we can detect some place which is more or less a good hit. This is the mean squared error. And yeah, you can see that there is some minimum around here. And that would be this displacement that we are working with. And the result should be -15 and 15. And looking at this correlation, this mean squared error, you can see that we have a nice hit here as 15 and -15. So that should be a good hit in this case. We can also look at the sand grains that I showed sometimes. And here I did a displacement of 30 and -20. You can see in particular, looking at this tip here, that it has been moved. And again, looking at the correlation in the Fourier space, you get a very clear peak. There is not much ambiguity in this case. The peaks will of course be affected if you have noise, then they are less pronounced because the noise level will just add a bias to the whole image. But in this case, we got a pretty nice hit in the data. So now we have learned how to find the positions, and one task that we often do is registration. And in this case, we have a sequence of images from the same patient taken at very different times. And as you can see, it's moving around a lot. And it's actually a typical workflow in diagnostics and treatment that you have to do new X-rays every, I don't know, week or so to see the progress of the treatment. But then the images land up like this, and it's not always so easy to compare, and particularly not with automatic methods. So what the task of the registration is to find the displacement and rotation, and then align the images so they can land on top of each other, and you can do good comparisons. And the process is that you have one moving image and one fixed image, and then they are moving by translations and rotations to interpolate into the grid that is common for both of the two. And this movement is done or compared using some kind of metric. And for the whole registration process, we also need an optimizer that tracks us or guides us to the optimal solution, because doing it the brute force is usually not a very good idea. Then it takes way too long, and it's probably not very reliable either. So typically what we have is a little algorithm looking like this. We have a moving image and a transform. So, and then we do some interpolation. We compare it to the fixed image, and then we get some number out of the metric when we compare the two. This one should be also visible. Yep. A little bit more complicated workflow would be to actually wrap it up a little bit, where we include an optimizer to the transform, and then we can loop around here until we have a good fit with the metric of these images. So we have two images, the fixed and the moving one, which has been distorted in some way or displaced in some way. And we want to match this as close as possible. And that is done using different transformations. We have here a list of those, affine, scaling, deformation, shearing, whatever can be needed. Some of these are not needed because the sample is not changing in that way. Then you can exclude it, but it's often for robustness, it's often good to actually add more possibilities than is needed due to noise and variations. Then we have different interpolators, nearest neighbor interpolation, bilinear, bicubic, B-spline, etc., etc. There are quite many ways of doing the interpolation. And finally, we have different metrics to work with. Mean squared error is easiest to compute, but it may be not so exact to do the match. And then we have structural similarity metric or correlation factors. So we have a collection of different metrics, and in the end, you probably have to experiment and see which one makes most sense for your application. And then we have optimizers. Actually, these optimizers, they are also used in machine learning context. So we have gradient descent, Adam, stochastic gradient descent, and so on. And by saying machine learning, we can actually create a registration tool using TensorFlow and see that as learning case, actually. And then we get some kind, then we have actually this same grid that we did before. And then we can try having these two images and see what happens. And you can see that it's trying to optimize and moving around, but it's not really doing a good job. You can see that it's still displaced. It's trying to find something, but it's not really doing well. That was the mean squared error. And then we can try actually a different case where we have a smoother gradient. So instead of working with the grayscale images themselves, we apply a threshold and then compute the distance map on the images. Unfortunately, there was some problems with my code. Probably version clashes or something. So I couldn't run this as a simulation, run this fitting, but this should actually produce a much better result on the registration. Yeah, that was the failing code somehow. But we can also work with structural similarity index. And you can see that it converges pretty quick, and then it stays on a certain position. But this position is not ideal. It's trapped in a local minimum, because you can see here that there is still a displacement in the error curve. So depending on the images, you have to use different types of metrics and optimizers. And in particular, if it's like this, it was a random field, it's very hard to get a good registration. So now I showed you a way how you can build up the principle of a registration tool, but mostly there are actually predefined code to do this. And in ITK and simple ITK, there is a lot of algorithms to do it. And here is a piece of code that does the registration for you, where you set different images, fixed and moving images. You set which kind of transform you want to use, also some initializer, and then we set the metric as mean squared, or as matters mutual information. That's another kind of metric. Then which kind of algorithm we want to use, brute force or simple, the metric sampling strategy is set to random. So there is a lot of details in this code. I'm not actually going to describe everything. It's even longer than this. But the idea is this function here sets up the registration task for us. And if you want to run this on, for example, the sand images that were displaced, you can see the difference before. It was quite a big difference between the two images. Then we do the registration, and the output is still a little bit displaced, but it's getting closer to the real thing. So we may change something about number of iterations in this fitting to get the last piece right. Another thing is to work with the correlation is to look at displacement fields within the image that can actually carry information about what's happening in the process as well. So what we are doing is to do local correlations. So we look at this piece here, and then we correlate this box with a neighborhood, and then we see in which direction objects are moving within the image. This is not like before when we had grains that we identified, but here we really look at the gray level distribution, how it moves around in the image. And that can be used in a physical concept where we work with the digital image correlation and digital volume correlation. And what we want to do is we have some kind of correlation term, correlation term, and we have a deformation term. And this deformation term is actually describing the physical properties of the object. And this one was a lot of text. Let's skip that one. And what we can do with the help of this is we can actually quantify the deformation in the sample working with a strain. So we want to look at the relative displacements within the image. And that can tell us then if we do some kind of pull or push test, how the object is changing over time in the images. And what we can get is the strain tensor, which tells us how the whole object is displaced. An application is, here we come to different types of strains. So we have the different parts of this strain tensor. One is about the changes in size and scale of the object, and the other one is changing of proportions within the object. So these two are described within the strain tensor. And here's an example about, this is, I think it's sandstone column, where they had put some notches, and then they applied a force on the sample to create a shear band. And in the images, as they come, you don't see much of changes. You don't see anything here in the raw images. In the tomography, you don't see much. But if you start doing the time series analysis with digital volume correlation, you can actually quantify the shear band within it. And if you want to render it, you can also put it up like this. And this was mainly done using X-rays, but at the same time, they also did a neutron experiment to see that the water transport was behaving differently along this shear band. And yeah, that was all for today. We have talking about different approaches how to do and plan experiments for dynamic experiments. And for doing that, we have different approaches to analyze the data. One is object tracking, requiring segmentation. Can also do registration to be able to analyze the images that comes in the time series. And finally, we looked a little bit on digital volume correlation, which is a large topic of itself. I don't think I put up a reference on it, but there is even a book on this topic specifically. Yeah, that was it for today. And stop the